little samba on me.
Oops.
Oops, wrong one.
Welcome, ECS 16A. Woo!
All right.
Very good.
You're
Now
on.
I have to turn my brain on to English again.
Por qué?
Today my accent will be stronger.
Oh yeah, circuit.
Right, I have to learn Hebrew accent.
That's not a problem, Anna. It's very, very, very easy.
I know. Especially for you.
Especially when you get tired, it's no problem.
I know. We did it. Okay.
All right, let's do it.
Let's do it. Yes. All right. The day after the midterm, we have 240 people here. We're doing well. Yeah.
Oh yeah. 242 brave souls.
Okay. Very nice. Well, now you need to switch your heads to module 2. And we were told by the TAs that sometimes the students, stop coming to lectures to study for midterm. And so everybody should come to lecture because this module, the circuits module, is going to pick up, and we don't want anybody, behind. So come to office hours, ask questions. And we keep going.
Oh, good fire show next lecture.
There will be a very good show next lecture. Yeah. Even better than normal, right, Mickey?
Oh yeah, absolutely. Oh yeah, fire, explosions. Oh my God,
everything. Good stuff. Yes. But don't spoil too much. The element of surprise is important too.
Okay, sure. Yeah.
Okay. All right. So everybody survived the midterm. Here we are. Let's rethink here what we learned in the last lecture. Last lecture, we were talking about the touch screen with resistive components. So we went quite far in our analysis where we started off with two plates or two materials, which we looked at the properties of those materials. They were resistive materials. And we modeled this touchscreen, which you will start in the lab next week, building your own, which is pretty cool. And we modeled it first with wires, and then we came to our final model last class, where we had an array of resistors as shown here. And I think that by now you can kind of tell that our models are always going to be a combination of all these elements that we are defining and we have been using. So we defined open circuit, we defined wires, we defined resistors, and then we have sources of energy, which was a voltage source or a current source. So for our touch screen, resistive touch screen, our final model was an array of resistors where we had these bars at the end of each plate where we would which we use as connectors. And we looked at how we could apply a voltage to that bar, to the top and to the bottom plate of our system, and measure voltage across elements. In order to get to this array of resistors, we actually came through different circuits or different blocks that we defined before. One block that we used a lot in last lecture was the voltage divider, right? And the voltage divider was great because divider, it gave us a tool to look at the potential between two resistors. And we saw that we could get measure. We saw that we could measure the potential here between two resistors that were connected to a voltage source. Then we also looked at a different block, which we call interesting circuit. And the interesting circuit was interesting. Why? Because we saw, do you remember? Let's see. That's right. Oh, Adam is there. So we saw that the interesting circuit was important because when we had an array like this, and we wanted to measure, first we saw that the potential here and the potential here would be the same. And because the potential between these elements was the same, that meant that there was no difference in potential. No difference in potential means voltage equals 0. So if the voltage equals 0 across a resistor, we know that in a resistor, voltage is the resistance times current. So if we have no difference in potential, voltage is 0, that means the current is 0. So that's what Adam was saying there in the chat, that we figured out that it didn't matter. And that's why we called this circuit an interesting circuit, because it showed us that we could still measure the potential between these nodes here. And then we knew that the potential was the same across these nodes, and that there was no current going through here when we connected the top plate. And in our model, the top plate was red. That's why I'm doing here in red. Last class, we only used three lines to analyze this, and it was a 3x3. So here is a slightly bigger. Okay. Ring a bell? Okay. What else was interesting? Okay. When we were looking at this at our smaller circuit, and we figured out that there was no current flowing through here, we said, oh, you know what? This is a nice way of, we can use another element to model this, which we said, okay, if the current is 0, because we figure out that the voltage was 0, we could actually in our model say that that resistor was working as an open circuit element, right? So this is what we did last class. Then, of course, our goal was, if I touch the screen here, I want to measure the position here in the top plate, which I'm here calling Y direction. And I also want to know what's the position here in the bottom plate so that I know exactly where I'm touching the screen. And we are doing that by measuring voltage somewhere away from where you're touching the screen. Good. Then what did we do? Okay, so first for our top model, or for the top plate, we came out with this this solution, which was very similar to what we did for the voltage divider, where we said, okay, UMID, which we were calling U touch, is L touch over the entire L. And here I'm calling vertical because the top plate, we were saying, okay, this is a vertical model, as I'm showing here, times Vs, which is the voltage that we apply across this, this array of resistors in order to find out where we are touching. Okay, questions so far? Does this ring a bell to everyone? If you haven't watched the class, then please do watch last class because it's important. How do we know RS? Okay, RS and R touch are the same. Actually, we don't. What we did was we just assumed, and this is really Skull black up, please. Okay. This is really done last class. But what we assumed last class was that we were going to, since this is a whole material, right? It's a sheet, a conductive sheet. So it's everywhere is conducted, badly conductive, but conductively. That's why we just modeled it as resistors. And we said, because we are going to model as resistors, as if we were cutting with scissors and making little wires out of it, and just modeling this could be an infinite amount of wires, then we model it as resistors. And we said that all these resistors should be the same because we were making an equal array here and we were using the same material. So it was always like a bad conductor versus a better conductor, right? Where our bars here were really good conducting materials and the top flexible sheet was not so well conducted. No, our press does not go entirely horizontal. No, it's just a point, and we always modeled as a point, and that's why we were always measuring the in a certain point in the array. We're not squishing, otherwise it would give us no information, right? The point of these touch screens is that you select something. So the touch only happens in this point where we make a connection between the top plate and the bottom plate. Does anybody remember how we modeled this connection? What elements did we use here for this connection? When we touch, what was the element that we use? A wire. Very good. Very good. Okay. The third. Okay, so I'll move up. I'll move down. Then our second part of the analysis was the bottom plate, because we really have this crossing parts. So now when we attach the bottom plate, that means that current is only going to be flowing here through these connectors, where the black part here, it was our bar, very conductive, where we make our connections and apply VS again. Now here is a different material. It could be a different material than what's used in the top plate, but the model that we used was the same. We said, okay, it's not a perfect material. So let's model it as an array of resistors that we know that current will be flowing through these connections or through these lines. Same analysis was done when we said, wait a minute, this is really similar to our voltage divider, which was also very similar to our interesting circuit where we derived that there was no current flowing through this in the bottom plate. So that's why our model now can be this array, this crossing array of resistors, which we can address bottom and top and figure out exactly where you're touching by measuring VS outside in this these bars. Okay, this was the model that we arrived at last class. So today, what I want to do is to give you more tools so we can keep designing cool stuff, because that's the point of this class, right? And because I am aware that these material circuits might be new for most of you, while lots of you had linear algebra before, I encourage you to unmute yourself and ask questions, okay? Because it's hard for me to follow the chat, especially when the chat has random things going on, okay? So
we got it for you. If there's a good question, we'll also can erase it for you too.
I know, but
okay, fine.
Yeah. Basically, if you're thinking I'm going too fast, it's your job to slow me down, okay? All right. Otherwise, I'll keep going because I like talking a little.
Oh, yeah, we know that.
Not as much as you, Mickey.
That's true.
Okay. Let's move on to a new concept, equivalence. I want to talk about equivalence. Well, during all these classes, I have been actually giving you examples of equivalences without really calling it equivalence, because if you give a fancy name, then people go, oh, what is this equivalence? No, but I have been using it. Even today I used here where I said, oh, in our model, we decided that there was no current flowing through here. Therefore, if there is no current flowing through here, we can model that resistor as an open circuit. This is pretty much what equivalence means. Today, I will define equivalence very more formally, which is the following. If you have two circuits or two elements or two circuits, you can call them equivalent if they have the same IV relationship. So if I can draw an IV characteristics for different elements or different circuits, and I get to the same IV characteristics, I can say this circuit, these elements are equivalent. Okay, so let's start off with our good old elements that we have been working on, and then we are going to build on from there. First, let's say I have a voltage source. Okay, so in the first class, we drew the current relationship for a voltage source. So if I were to, for those who didn't come to class, here's a review. So if we were to draw the IV characteristics for a voltage source that is giving us a voltage, a set voltage of Vs, how would my plot look like? What would be this plot? A vertical line. Thank you, Omar. That's right, a vertical line. And we would say, okay, this is the vertical line. And right here where it crosses V, we have Vs, right? Now, let's say I tell you, you know what, in this example, I'm going to say that Vs equals 0. Well, if Vs is equal 0, how would my plot then go? What would my plot become? Here, the IV characteristics for, yes, that's correct. So if I say Vs, if I say Vs equals 0, that means that my plot would look like this, right? Everybody following? Well, which element has that plot? Same as a wire. That's exactly why. That's right. So if I were to draw the wire, do the same analysis for the wire, where here I have wire. And in your notes, actually, the wire is going to be sometimes called short circuit. And I think last class there was somebody that...
Oh, there was a movie. There was a movie called Short Circuit too.
Oh, yeah?
Yeah.
I can always tell when you're bored, Nikki.
I'm not bored. This is exciting. You took one element, a voltage source, and then it turns out into a wire. Crazy stuff.
I know. Isn't that amazing? Okay.
The same thing. Same thing, but not.
Same thing. So because
same, but
here,
different.
Okay, when Vs equals 0, that means that the voltage source and the wire have the same IV characteristics. So we can say that they are equivalent in this case. Equivalent. But there's a condition, right? I said that the voltage source had to be set to equal 0. Yeah? Good? Okay, there are other examples that we have used that I can show you the equivalence. Let's do these simple elements and then we go to more complicated ones. Okay, another example. Let's take a current source. And please be clear that both current source and voltage source, they are not variables in our system, right? They are given. So if I take a current source, IS, and then I come here and I draw the IV characteristics for a current source, how does it look like? Who remembers? What does the IV characteristic for the
horizontal line?
source?
Horizontal line. Horizontal. They say this horizontal line.
They say it's a horizontal line. Very good. So I say here, okay, this is horizontal line where it crosses here the axis. This is the value of IS that is going to be set, because you go there and set. You have worked in the lab now to know that you can set the voltage, set the current, right? Okay. Now, if we do the same thing and say, okay, I will set the current to be equal 0, the current from my current source. If we do that, then just like we did with the voltage source, we are going to bring IS here when, oh, sorry, that's not good. Let me make my line thicker so I can hit the axis. Oh, much better. So I'll bring IS here, and that is going to be when IS equals 0. What element looks like that? If there is no current, thank you. Very good. Oh, I like it. I like it much better with this type of participation. This is an open circuit. I figured out, Miki, that my handwriting becomes better if I use very thin pens.
Oh, yeah?
Mm-hmm.
What's the magic?
It's just that it becomes better.
Wow. And then you write in capitals. Oh, it's like so offensive.
Yeah, that's for you.
It's like, oh, open circuits, like you're shouting it.
Exactly. Okay. So if I had to draw the open circuit IV characteristics, it would be like this. This is in our first class, right? So what does that mean? If I zero my current source, then I can say, so if IS is 0, I can say that the current source and the open circuit have the same IV characteristics. And because they have the same IV characteristics, I can say that they are equivalent. And we have been doing this, right? We have been doing this all the time. Whenever we do circuit analysis, we go around and we say, okay, oh, look, there's no current here. This behaves like an open circuit. Oh, there is a wire here. That means that the voltage across the wire is 0, right? This was the very first class. Okay, now, other examples. Or why is this important? This is important because you are going to be designing things, right? You are going to one day get a job or get a project where you are giving a set of requirements. And I will say, okay, design circuit 1 such that the output of circuit 1 will be X and Y so that it can drive circuit 2. This is a possible design. So if I had here, if what I gave you was a task to design, oh, okay, I'm going to start using circuits like this, short writing, okay? Circuit 1, and then I am going to connect this to another block of circuit, which I'm going to call 2 to be creative. Then how do these circuits know of each other's existences? They only know of each other's existences because we will have, if we take a point here where there is a connection between them, we will be able to measure a voltage across, which we call V out. It's coming out of this block or this box that we are designing. And we can define that there will be a current, which I'll call I out. right? And then, okay, you have to do circuit analysis, you have to do node analysis to figure out how to build circuit one such that it gives the appropriate I out and V out to drive circuit two or vice versa. That could be a design. Now, if you do this and then your boss or you realize that, you know what, I should have done a little tweak here, and I want now to improve my design by building a separate circuit. Well, now you can actually, by knowing what is the optimal output of the circuit, you can use that simulation to build a new circuit without having to build all the equations again. The only thing that you have to do then is to make sure that when you do your second round of optimization of your design here, and you're building your circuit tree to connect with the load that you were told to connect, or with the next block that you were told to connect, circuit 2, you have to make sure that as far as circuit 2 is concerned, this I out and this V out here is exactly the same. And then things don't need to be changed in circuit 2. Because if you build circuit 1 such that it's equivalent to circuit 3, as far as circuit 2 is concerned, everything is the same. But you might have optimized power consumption, you might have optimized number of elements, you might have realized that, you know what, if I make this simpler, I'll make less mistakes, it will be simpler to fabricate, it will be done quicker. All sorts of things could be happening. All you need to do, because you know equivalence, is that the IV characteristics has to be the same. And then circuit 2 will be happy. Okay? Now, IV characteristics. The IV characteristics for a typical block, as we have done so far, could be, or the IV relationship could be several. We saw that in some cases, the IV characteristics, it's like this. In some cases, the IV characteristics is like this. In some cases, the IV characteristics is like this. We could also have IV characteristics. Let me pick a different color here. IV characteristics that could be something like that, right? And this is just a combination of elements. So if we had to label them, we know that this horizontal line here is like this, like that. Okay, so what's the green horizontal line? Everybody needs to be this like I source, that's right. Yes. And then the horizontal, the vertical line here is our V source. What is this line that is going here right by the, that's a resistor, very good. And the resistor, we know that the slope of the resistor is the inverse of the resistance, right? And what is this odd line here? This one. It crosses the I, it crosses the V, not in zero. What is this? Very good. It's a combination of elements, a resistor plus a current source. Where in this case, the resistor is giving us the slope, right? And here, where it crosses the I axis, it's given by the current source. So we can represent our elements, the elements that we have now, always with lines, because we are only doing linear circuits, right? And we studied linear algebra, so we know that the IV characteristics in this class is always going to be a line. It will change as you go to different types of circuits. Not all circuits are linear, but here they are. All right, so we are going to make use of this. And the message here for our design is as long as the IV relation is the same, we can say that circuits are equivalent. And that is going to be so useful for us because we can make things much, much easier this way. Okay, let's do an example. Because I always learn better with examples. Could you use linearity on blood flow in the human? Oh, deep questions. Okay. Oh, I need my better. Okay, so I will draw a circuit here and we are going to do the analysis, a simple one. So let's say we have our voltage source, good old voltage source Vs. I'll connect to a resistor. And this is part of design. So I know that my resistor is R. And what I want to know is what would be I element and what would be V element when I'm doing the analysis here, such that I can figure out what's the equivalent circuit for some building block. Okay, so if I had to ask you, what is, how does the IV characteristics look like for this simple circuit, where we could, when I do this, when I define these I elements and these V elements, I'm basically looking at this circuit as a block, just like I told you here, as a circuit one, where it doesn't matter what's inside, but here I'm telling you what we're going to work on, which is inside. And I want to know what is I element and V element. Let's see, do you have the intuition? Do you have the intuition to tell me how the IV curve would look like here? Perhaps if you unmute yourself and say, okay, it will be a line crossing here and crossing there, it will be easier to understand than just the chat.
Yep.
I have Vs over R, question mark. IL equals 0, V element equals Vs. Could be, oh, I have no idea. That's also a valid question. And that's why you come to class. Because if I am asking, high probability that will give you the answer. But I want you to become more useful, more used to thinking. Let's see, a line with a slope 1 over R. That's a very good, answer, because we know we have a resistor shifted to the right. Okay, let's do this. We are going to get there. Okay, so we know how to do KCL and we know how to do KVL. So let's use the tools that we have now. So how can I write a V element in this case? I can say that V element is going to be equal Vs plus Vr, if I go this way. Make sense? Makes sense to Miki. Makes sense to one person in Anastasia in the chat. Okay.
Nobody can nod their heads,
300, 300, 300, 300. Okay. Yep,
If a person nods their head without a camera, did they really nod their head?
You don't
If
know.
a tree falls in the forest and nobody heard it,
Oh,
they really saw it?
Seeing. Okay, so it makes sense. How did I get there? Oh, if you are not seeing it, remember our analysis. We go, okay, what's the voltage across the resistor is here, plus the voltage across that is given by the source is going to give the voltage that we measure here, right? That's what we have been doing in class so far. So let's apply the element definitions to write this. Vs is a voltage source, is a given, plus Vr. Vr is I element times R, right? Because I have this current I element here that I am using to test this circuit, and then I'll have I coming through here. Well, now, and all I want here is to find the IV characteristics so that we can represent current with respect to voltage in our circuit. So from that, I can write that I element is going to be equal 1 over R, like was in the chat, VL. V element plus, minus Vs over R, right? I just manipulated this equation, put Vs to the other side and divided by R. So now we can figure out where are the points where our line is going to cross the current and the voltage axis. So let's say, if I say that, well, how would you do this before I give you the answer? You can either say that the current is 0, or you can say, oh, when the voltage is 0, right? So if I say when the current is 0, then I find the place in this IV relation where my line is going to cross the vertical axis. When the voltage is 0, it's going to cross the horizontal axis. So, okay, so I'll find that when the voltage is 0, my line is going to cross this horizontal axis right here. And what is that value going to be? Well, you just go here. So voltage equals 0. That means that if V element, okay, I'm doing V element. If V element equals 0, that means that the only voltage that I have there is Vs, right? And then, very good. Now I zero the current. So I come here and say, if the current equals 0, that means that the value here where it crosses the I will be minus Vs over R. So now we got the slope and we got where it crosses. We can draw our IV characteristics, which is a combination of a voltage source and a resistor. Sounds good? Everybody following? So if I now design another circuit that has the same IV characteristics as this one, then I can say that they are equivalent. And that can be as complicated as you want or as simple as you want. We are always going to give you something complicated and make it simple. Okay? Well, there is a method. Why is it minus Vs? Yes. So you set V element to 0, and then you know that the current will be 0. Then you're left with this, which is where you would cross when I is 0. Okay? Very good. Thanks for answering in the chat. Now, there is a method that you can use now to come up with these equivalences. And it's really a methodology that if you follow, you can really simplify your life. And okay, so they're called here the Thevenin and the Norton equivalent. And what's the goal? What's the goal?
Oh, good stuff.
Oh yes, I love this stuff. You forget about it, right? It's so useful. You don't, okay?
No, I don't.
So I have a circuit here, and
so important. Would never forget it.
Right. And our goal here is always to get I element and V element or V out, because then we can represent other things. Okay, so the methodology here is for you to come up with the simplest circuit possible that you then build equivalences to, or you simplify your model to that equivalent circuit. And we have done this without having this language, right? Where we simplify the array of resistors with our voltage divider. So here we're going to show you the methodology. Okay, so what do I do? What is the simplest possible circuits that one could build? Well, we could take a voltage source and a resistor, because I only need 2 points to build my line, right? And then I need to set the zeros and find out where the line crosses both axes. So now for the Thevenin equivalent, we use a voltage source and a resistor. And now I'm going to call V Thevenin and R Thevenin. Then I will have, again, I will draw in red. I'll have I element here and our V element as usual right here. Okay, this is the circuit we just did, right? But there is another circuit that you could draw that it's quite simple. What's the other combination? What's the other linear combination that you can use here to build an IV characteristics? Thank you, that's correct. We can use a current source and a resistance. Well, if I have a current source, which I will call, well, I will name this later. This is the Norton equivalent when you use a current source. So I'll call the current that's given I Norton. The resistor, I will have resistant R Norton. And then what else do I need to define here? I need to say, okay, there will be a voltage across here, which will be V Norton. Okay, so let me just name them. This is the Thevenin equivalent, and this is the Norton equivalent. Okay, now let's see how they are useful for us. I know that for the Thevenin equivalent, we already know how to build the IV curve. Why? Because we just did it. Okay, I will actually do somewhere else so that we have space here. It's what we did right here, right? But now I just have different names for it. So if I had to draw the IV curve for the Thevenin equivalent, it would look something like we just drew, like this, where now where it crosses 0, I'm going to call V Thevenin. And here, since it's this circuit here that we are using, we are going to label this point here. Let me put it right here, minus V Thevenin over R Thevenin. Just changing the names, same circuit. Why am I doing this? Because this will give you more, in the Norton equivalent should be V, yes. It's V elements, but I'm calling V Norton. It will become, okay, actually I'll jump there just so it becomes more clear why I'm doing this. In this methodology, what you do, you say, okay, intuitively, what we did here, we said, okay, first we are going to set the current as 0, and we also set the voltage as 0 in order to find out these 2 points, right? So the methodology does exactly that, where you have a circuit, you take any circuit that's given to you, and you say, you know what, I'm going to say that this circuit has 0 sources. That's the first thing that you do. And then you connect this circuit to a test. Just like I showed you how to test, how to measure voltage and how to measure current, we can do the same here, where I'm going to connect this to the outside world, and I want to test things. So to test, I could hook up a voltage source here, which I'll call V test. And by hooking up this voltage source here, I know I'm going to have an I test. And what I want to come up is with an equivalent circuit that will give me R Thevenin. So, and I know that R Thevenin is going to be equal V test over I test. Why do I know this? Well, because our equivalent circuit here is given only a resistor and a voltage source. So I want to come up with an IV characteristics that's going to be equivalent to that circuit, which means that when I do my analysis here, I get that the resistor that I'm using and now calling R Thevenin is going to be the voltage that I am applying divided by the current that I can measure, right? So how does this look like in our analysis here? And we did this just with intuition, and now I'm doing more formally. We say that, okay, V element is equal our V open circuit, because what we did, we set V to 0, right? So if you want to write a set of rules, we can say the first thing that we're going to do to find this equivalent, yes, Jay-On, we are going to get there. Please wait. It's coming to you. Okay, so the first thing we're going to do is to find V Thevenin. And how do we do that? Well, we use our other equivalents, right? We say, okay, if I connect an open circuit, if I connect an open circuit, I can find V Thevenin, because once I have an open circuit here, I know that I is equal 0. And that's what we did to find here, right? We said, okay, when I equals 0, we find V Thevenin. That's what we did right here. Okay, the second thing that we did was what? Second, we find our Thevenin. And how? Why do we find that? Because if we find our Thevenin, we are, in practice, we find the slope. And how did we find the slope? We zero out the independent sources. So I will say independent sources, both current and voltage, right? If I have current or voltage source independent, I will zero them out. This is what we did. Okay, if we zero out the Thevenin, that means we can find the slope, because now all we have is the resistor. If this part here is zero, that means there's no source. So when I'm measuring out here, I'm going to be getting the value of this resistor. Okay, so this is the methodology. And then we get to this plot, which is it's the simplest possible equivalent circuit that we can get. Now, there was a question directly to me saying, are we going to do this for I Norton? Yes. So to do the Norton equivalent, it's the same methodology. So let me go back here to the methodology. I said, okay, I can have this circuit here, which is some circuit that I have control over, and I'll say, okay, I'll zero the source. I will apply voltage, measure the current, because I know that once I zero the source, I can write that the resistor, our Thevenin, is going to be V test over I test. The other practical way that one could do this test is you have, again, a circuit with zeroed sources. And then outside here, I could apply current and measure the voltage, right? So I can come here with a current source. Where I will have I test, which I know, because I am setting that. I'm coming with an apparatus to measure that. And then I can measure the voltage across here, the element. Well, if I do that, what's our Thevenin? If instead of taking an external voltage source and I take a current source, what's going to be our Thevenin in this case? Questions? Come on, come on. If I am applying a current to test, if I'm applying a current to test, I'm measuring voltage to find an equivalent circuit for a circuit that has no source exactly. It's also going to be V test over I test. So, okay, here I call this our Thevenin 2 just because we are used to it. But actually, a circuit here, when we have a current source, is called the Norton equivalence. So I am going to just rename here to R Norton. Why? Because I'm using the current as the test, okay? And when we define these two nice equivalent circuits, what's the difference between them? Thevenin uses a voltage source, Norton uses a current source. So here, when I am selecting my test, my V test, I test in the lab, if I use a current source, I'm going to measure the voltage, and the equivalent resistance of that circuit is going to be the R Norton. And if I take a voltage source and I measure the current, the equivalent resistor of resistance of that circuit is the R Thevenin. We're going to use this a lot, okay? So now the question in the chat, and I will ask that back to you. So if I had to ask you, what is the current in R Norton, which was a question that came directly to me on the chat. So what's the relation between I Thevenin and I Norton, V Thevenin and I Norton? It's right here, right? The answer. Well, if we use this test, they are both V test over I test, V test over I test, and they have to be the same because we're saying they are the equivalent circuit. Why? Because they're going to have the same IV curve. So here I'll have V Thevenin, and then here I'll have I Norton. Beautiful, huh?
Gorgeous.
I think so. Okay, they're very good questions here. One question is, what does it mean to zero a source? It means, you know, when you go to the lab and you have to set the voltage across your measurement. You set the voltage to 0. That means there's no voltage coming out of your circuit. So if you set the voltage to 0, that means you zeroed the sources. Or you can do the same with the current source. In other words, it means that you are doing an open circuit, right? And that's what it means to zero the sources. You are actually saying, okay, this is going to be 0. My independent current source is 0, or my voltage is 0. And that's what it means here. Okay, and then when you apply this external voltage and this external current, then you know exactly that's what is inside here. There is no contribution from another source. It's only the source that you're using to test. Did I answer your question? Great. All right. Okay. Put this in your pocket because this is something that you're going to use a lot to analyze circuits.
Wow.
Yeah, clear? Okay, I shall continue then. Why could I do this? Well, that comes from math. And you guys spent, many hours studying for the midterm yesterday, and you mostly focused on the linear algebra. And the circuit analysis methods that we use also uses linear algebra. And I think this was in the midterm, wasn't it? This
Yep.
text here.
Well, hold on, let me check. It's been so long.
Yeah,
hard to remember.
So. Yeah. What? The professor put things from her slides in the midterm? Shocking. Okay. So our methodology for circuit analysis was.
I thought you were doing circuits, Anna. It's like I think you're going over my turf here.
Sorry.
What do you think?
No, there is no your turf and my turf.
I'm just messing
with. Okay. So you're distracting. So we have to find a vector of unknowns. In our case, the unknowns have been always currents that we can label I1 all the way to IM. All the currents that we set, we take our V elements and we set a current, we follow the passive sign convention. Other unknowns that we have are the potentials, right? And the potentials, we name them, hold on, let me just make my vector a little bit longer. They are the potentials that we name in the nodes of our circuit. So U1 all the way to UK. Okay, so that is our vector of unknowns. Then we set a matrix A, and that matrix A is what relates our unknowns to another vector, vector B, which is the vector of knowns. And the knowns in our circuits have been always the sources, the independent sources. So I can have IS1, I can have IS2, and then we could have voltage sources, VS1 all the way. Yes, Mickey?
VS2 maybe? VS2? Oh, VSN.
Yes, well, let's do it even nicer. We can say it can be VS, actually, it's not one. Even I did my notation wrong. This is L. So I'll say VSL, VSL2, and then VS1 all the way to VSM plus K minus L, which will get our dimensions here correctly. Okay, now we would write this as our equation was we had a matrix A, which relates the unknowns from vector X to the stimulus to the given parts of vector B. Well, because they are linear independent, we can write the solution for this. And the solution was that X is the inverse of matrix A, remember, from the midterm, times vector B. This is the solution of our system. And it did that for math, for all sorts of applications. Oh, it works for circuits too. So now, okay, we are engineers.
Shocking.
And now,
Shocking.
I know.
Like, no, physically, like shock. Shock.
So now we are engineers, and we want to know what's inside. What's happening with all of these unknowns? And we know that they are going to be relating to each other. So every independent source that we have here is going to have an effect on all of our unknowns through relations that we are setting in matrix A. So let's say if I had to write an expression for a current II that I'm calling here, and a relation to all the current sources that I have in this system, I can say, okay, the relation will be some constant, which I'll call alpha 1 times ISL plus some more components, depends on the dimensions that we have here, alpha L, ISL, and then we will go all the way to the lowest, to the highest dimension that we have here, which would be alpha M plus K times VS M plus K. Okay, you can do, following me? I'm just taking one unknown that we have here, and I'm making the multiplications, right? You have to go like this, like that, and relate to your other vector. So this is what I'm doing. Okay, I can do the same thing for you, for potential, and I can express this potential. So I'm going to as a sum of this. And this is exactly how you did your vector matrix multiplication, right? So, okay, so I go here, beta 1 IS plus all the way to beta M plus K vs M plus K minus L. Okay, I'm making just the dimensions work. So the point of this methodology and the linear algebra that you learn is that I can express the variables in a circuit as a linear combination of sources. Which is the result, the solution that we get from this setup for the circuit. Well, if I can express this as a linear combination of sources, that means that mathematically, let's say, if I want to find out how much I1 is, I can say, okay, I will first calculate a part of my circuit that has IS1, and I'll make all these parts of the circuit equal 0. Why can I do that? Because they are linear combinations, so I can first calculate this part, and then calculate that part, and then calculate that part, and then at the end, I sum them, they are linear combination, and I get I1. And that makes circuits life much, much easier, because you can just say, okay, I will set this source as 0, and then I solve the rest of the circuit. And then later, if you have many, many sources, which is what we are going to do, you can treat each one of these sources separately and find the parts of the solution and then sum them at the end. So if I were to write this I here, it would be quite nice, because I will have, okay, I1 over some plus this IIL plus la la la, which means that I will have this alpha IS1 term completely independent of that alpha LISL. And mathematically, as I said, if I make this go to 0, I can find how much this term is worth. Then I make this one goes to 0 and analyze this term. Sum them, I have the solution. We can only do this because our circuits are linear, okay? Only resistors, right? Resistors, wires, and sources. And that's why our unknowns are always the currents going through the elements and the potentials in the nodes. Sounds good? Well, I have been doing this all along. You didn't complain. Only one person says, what does it mean to zero a source? Well, this is what it meant. The fact that I can use this linear combination 0, 1, just to make my life easier and move on with my analysis and then come back to it. So now we can do analysis of a more complicated circuit. What's the first reaction that you have when you see a circuit in front of you? Oh, circuit, I don't understand. No. First thing we do is label the things we know, right? So let's do that. We'll label the things that we know. What's different about this circuit? Now here I have 2 voltage sources. I have an open circuit here where I want to measure V out. I'm going to use this open circuit to measure something. And I have 2 resistors. Not too complicated, but different, because we never had 2 sources, independent sources before. Well, let's do this in steps. So first, what would we do? Let's label our nodes. So first I will do here 0, and I will label this node U1. Okay. Now, I can say that U1 minus 0 equals V out. Can I? Yeah, you're curious saying yes, yes. Yep.
It looks like only.
Yes,
Yeah,
yes,
oh,
yep, yep.
yeah. Yes.
Yes,
3 people
everybody
say
sees it.
yes.
Very good, very good.
Yeah.
Oh, if you don't see this, what do? You say, okay, I'll do KCL or KVL, and you will find, okay, the potential between these two nodes is equal to V out. So I will write here or later that U1 equals V out. All right. So now I have these two sources. I don't know what to do with them. So I will break them up. I'll say, you know what? I'll set 1 to 0. I will take V2 here and I'll set V2 to 0. So if I set V2 to 0, I can rewrite my circuit as such. So first step here, first step. I'm going to rewrite as I have voltage source V1, and I will have resistor 1, resistor 2. When I set a voltage to 0, what element am I using?
Ooh, I see a lot of wires.
Yes!
Oh, so many wires. Not enough wires though.
Nikki,
1, 2,
we're
3, 4, 5, 6.
we're teaching, and they are learning. Very good.
Well, 1, 2, 3, 4, 5, 6, 7. No, it's not enough. No, more
Okay,
wires.
very good.
More wires.
We connect a wire. So what was our first step here? Let me just write down. While you're thinking, start thinking about what's going to be my next question. Okay, so we compute a response to VS1, which is our, and we have the power to do this, okay? VS2, because circuits don't bite, and we think, so we have the power to do that. They shock you though. Okay, do we know the solution? And then if I come here and I say, okay, wait a minute, my problem was I had to measure V out in this circuit. What's V out? That's right. So voltage divider. So V out is going to be R2 over R1 plus R2 times VS1. Okay. Oh, this makes me so happy. Voltage divider. Many answers. Or you mid. Very good. Very good. You see, we do things for a reason here. So, question for you. What would be our second step? We can't get too excited and forget that our circuit was actually with two sources, right? So now our second step, we are going to compute a response to VS2. And we are going to set VS1 to 0. So if I set VS1 to 0 and I want to compute a response to VS2, I have resistor 1, resistor 2. Now I will have VS2 and no, not like that. VS2, and then right here on the part of the circuit where I had a voltage source, when I set a voltage source to 0, we just set this.
What does it do? What does it do? What does it do?
That's a wire, right? And now again we come here, measure V out. And what's going to be V out?
Voltage. Yes.
That's right. Okay, so now the solution is going to be R1 over R1 plus R2 times VS2. Okay, so
Wow.
this methodology of breaking things like this and zeroing a source with these mathematical tools that you learned before is what we call superposition. Okay, and superposition, it means that you can break the parts of the circuit and you follow these steps. You set all the other independent sources to 0. If you have a voltage source, you are going to replace that voltage source with a wire. Why? Oh, because we know that when the voltage goes to 0, it's equivalent to a wire. And look, now we have the vocabulary to sound really smart and say, okay, a voltage source that is equal to 0 is equivalent to a wire. And then we go back to our superposition slide. If we have a current source, we replace with an open circuit, because a current source that is 0 behaves like an open circuit, is equivalent to the open circuit. Then we compute the circuit voltages and the currents to each one of these sources, and we complete V out by summing the V outs. So the only thing that's missing here in our example is what? That we would say that V out is, I will call here V out 1, V out 2, V out 1, V out 2 will be the sum. Superposition, okay? We got to all this.
Isn't linearity wonderful?
It's amazing. I think it's amazing. Yeah, I'm so glad I am, going through this again after so many years of not doing this
circuit within a circuit and a circuit and a circuit.
Why not just use PSpice? PSpice is a software. Yeah. It comes
that does
from
that exactly. I mean, in some ways, right? Like it simulates basically the whole thing, right?
Right. That's exactly.
And also more advanced models too.
Right. That's exactly right. Okay. So this this circuit here is called a voltage summer. Voltage summer. Not as the summer and winter, but because it's summing the voltages. Okay, and then the only thing that is missing for us is to express V out, our total V out, in as a combination, with respect to the potential. So let's see if I can do this in practice. Okay, when I'm preparing the lecture, I can do now already, not good. I will copy and paste in the other slide so we can finish this. And then we move to something else. Never mind. Okay, I will finish here. Or actually, just in this, I will squeeze here, and then I'll give you better notes. So in order to finish this V out, now we can write, since we had that V out was U1, then we can just say, okay, V out is V out 1 plus V out 2, which means that here we have U1, and U1 is going to be, okay, U11 plus U12, which we have the solution here. So I would say U1 equals to R2 over R1 plus R2 times VS1 plus R1 over R1 plus 2 times VS2. And this is a nice circuit because it's summing the voltages for some elements here, or constants, that I could call alpha and beta, that are less than 1. How do I know that they are less than 1? Well, because they have the ratios of resistors. And we say, okay, resistors are of some value. So if I have one value and I divide by that value plus something else, I'm going to get a number that's less than 1. Same thing here. I have a resistor of a given value. I divide that by that value plus something else. I'll get something that's less than 1. But the interesting part here is that when I select R1 and R2, the resistors that I'm going to use in this circuit, I am already selecting alpha and beta because it's those numbers are pre-selected. So we know what alpha and beta will be because we know the solution for this circuit, and then you can use that to model your designs. Okay, so next class, we will do some practice and move on to different circuit elements. I have to stop here. Sorry, I have so much more to say. Why can we sum them? Why not subtract? What part? You could subtract if you find in your convention that a current is negative. That means that the current is going to be going in a different position. So when you do here your linear combination, you will have a negative sign there. So you would be effectively mathematically subtracting. Make sense? All right. Be good people out there. See you Thursday.
Bye, everyone.
Bye. See you in office hours.